Today's lesson is going to be about derivatives of natural exponential and natural logarithms. And these are kind of fun, not hard at all. I got a few examples to show you, and then we'll get started. So first is the rule for derivatives of natural exponential functions. So I like to put two rules. The one, if it just looks like the derivative of e to the x, and then one if that exponent actually has more to it, something like x squared or 2x or 5x minus 7, something like that. And we'll do some examples. But the derivative of e to the x is super simple. It's e to the x. Easy. But the derivative of e to the u power would be, you write it again, and then you multiply by the chain. It's always attach that chain. All right? So let's try a few examples here. So let's find the derivative of e to the 2x. So here's what I always tell my students. You write it again. Write the entire thing again, e to the 2x, and then multiply by the derivative of the exponent. What's the derivative of 2x? Well, it's 2. Now, I don't like the way that looks. I like my numbers to be in front. So I'm going to rewrite this as 2e to the 2x. And that's the derivative. Let's try it again. The derivative of 5e to the negative 3x. Well, if there's ever a coefficient in front, you just tag it along. You just tag it along. Okay? If it was 5x, though, well, that would be a different problem because now that's a function times another function. But if it's 5, the coefficient, you can just tag that derivative right along. So you're going to write this whole thing again. 5e to the negative 3x squared. And then you're going to multiply by the derivative of the exponent, which would be negative 6x. Now, you can put these two together, the 5 and the negative 6x together, and you can call that negative 30x, and then the e to the negative 3x squared would go right after it. And that would be a more cleaned up version of the derivative. Let's do that one more time. Okay, here's an e to the something problem. Okay, write it again. E to the 2x minus 5x squared. Multiply by the derivative of the exponent. The derivative of the exponent is 2. The derivative of this is minus 10x. And again, you could leave it like this. I like that quantity to be in front and then my e to be always in the back. That's just how I was taught, but that's fine. And again, what is happening here is that exponent e, that natural exponential function, is being distributed to each one of these. So you definitely need that bracket. If you didn't, you would just be multiplying the 10x with the e, but that e is getting multiplied to both of them. All right, now this one, well, that's going to be something different than number 2. Notice this was a 5, just the coefficient. This is a 4x, 4x. So this is a product rule because this is a function. So we have a f of x times a g of x. We need to do a product rule here. So let's do our product rule. So it would be first times the derivative of the second. So again, the derivative of e to the 5x, you write it again. And then you multiply by the chain, 5. The chain is the exponent. So first times derivative of the second times the chain plus second times the derivative of the first. The derivative of 4x is 4. All right, let's see if we can clean this up a little bit. So again, here's my group, here and here. I like my e's to be in the back, so I would do 5 times 4x would be 20x, e to the 5x. And then this I would just write 4 e to the 5x. Now, I'm fine with that if you want to factor it out, depending on what your teacher would like. From here and from here, we can factor out. Let's look at the numbers of 4. And I can factor out an e to the 5x. And then let's see what I would be left with. Well, 4 from 20 is 5. We still have the x. Those cancel. Now we're switching groups, so put a plus. And 4e to the 5x from 4e to the 5x would be 1. So either of these work, but this is a more factored form of it, but either will work. You'll still get full credit there. Now let's not forget why we do derivatives. Derivatives help us find slope of the equation of the tangent line. So let's find the equation of a tangent line to y equals e to the negative 2x plus x squared at the point x equals 1. So remember, two things we need to write an equation, a point and a slope. Point and a slope. Well, we actually have half a point here. How do I find any y value? Plug 1 into the original. Always plug x into the original. So what would that be? That'd be e to the negative 2 times 1, which is negative 2, plus 1 squared, which is 1. Which is really just e to the negative 1, or even 1 over e. So here's your point. Your point is 1 comma 1 over e. That's like a mathematics way of writing it. Engineers would write it with decimals, but mathematicians like it in exact form. All right, now we've got our point. Let's find our slope. And to find our slope, we take a derivative. All right? And to take a derivative of e, we write it again, and take the derivative of the exponent, the chain. Negative 2 plus 2x. Now we're going to plug 1 into this derivative. Well, we already plugged 1 into here. We just did it over here. So this would be e to the negative 1, if you remember. It's just right there. And then we're going to multiply that by negative 2 plus 2 times 1. Oh, well, what's that? That makes 0. So this 0 times anything is 0. So your slope is 0. So there's your slope. There's your point. Let's write an equation for the tangent line. And the equation would be y minus y1 equals m times x minus x1. So y minus 1 over e equals 0 times anything is 0. So another way to write it would just be y equals 1 over e. And then you're done. All right, so that's the derivative for natural and exponential. Very easy. Write it again times the chain. Write it again times the chain of the exponent. Now let's talk about the derivative of natural logs, ln of x, okay? The derivative of ln of x is going to be this, 1 over whatever that is, 1 over x. If it happens to not be an x, if it happens to be a 5x or another quantity, we call it u, we would do 1 over u times the chain. Or you can even put the derivative in top. Some people were like, write it like this, u prime over u. So let's test this out on a few examples. So number 1, the ln of 5x squared. So this is my u. So I would write 1 over 5x squared times the derivative of that, which would be 10x. Now, this is a fraction. I can reduce this. This would cancel to be, let's see, 5 goes into 10 2 times. And x over x squared, they cancel and you have an x on the bottom. Now, there is another way to do this problem. And I'm going to show you with my last 2 examples what we could have done differently and get the same answer. But that's just your general rule. 1 over whatever's next to it times the chain. Let's do it again to number 2. Find the ln of 2x squared plus 4. So write 1 over that, 2x squared plus 4. And then times the derivative of that, which is 4x. And so now you would have, let's rewrite it like this, 4x over 2x squared plus 4. I can reduce every one of these numbers by 2. So this would be 2, this would be 1, this would be 2. So a better simplified answer would be 2x over x squared plus 2. All right, what do you think we're going to do now? Obviously, product rule and a quotient rule. We always have to try those, okay? So let's do product rule for number 3. Why? Because it's a 5x times ln of x. So the derivative would be first, which is 5x, times the derivative of the second. The derivative of ln of x is just 1 over x, minus the second, just write it like it is, ln x, times the derivative of the first. So times 5. Now be careful here. That's not 5 with the x. That's 5 times the quantity ln of x. And then you put the whole thing. Oh, I'm thinking quotient rule. Look at that. I almost got it messed up. So let's simplify this out. So this should be plus. Whoops. First times derivative of the second plus second times derivative of the first. All right. Good catch right there. Whew. So let's see what we got. Let's clean this up. X times an x. X on top and an x on bottom can cancel, so you just have 5. And then this 5, I never like it to be in the back, again, because I think I can get it confused with it calling it ln of 5x. So I'm just going to put it in front and call it 5 ln x. And then really that's it. You can factor out a 5 if you want to, but that would be it and be done. All right, now for quotient rule, this is where I was getting confused before. Let's do quotient rule on this one. You are not allowed to cancel those. Again, anything next to an ln, you just got to leave it alone, unless you can do some properties. So quotient rule says denominator times the derivative of ln of x, which is just 1 over x, minus the numerator, whoops, that's supposed to be an x, times the derivative of the denominator, which is 2x. And again, this is its own quantity, that's its own quantity, all over the denominator squared. So let's clean this up a bit. X squared times 1 over x would cancel to just an x on top. This 2x, again, I like to bring it to the front. I like my e's in the back, my ln's in the back. And then this goes over x to the 4th. Now, this can be cleaned up more. This x, and this x can all cancel. Don't touch this. This ln of x can't cancel. But you can reduce all those x's. And you cannot just do x minus 2x and call it negative x. That's not allowed. Remember, this is a product right here. So it's like a binomial. You can't touch what's in that binomial unless they look the same. So I can divide out an x from each one of these. And your final answer would be 1 right here. The 2 would stay here with the ln x, and this would be x cubed. So let's rewrite that. That would be 1 minus 2 ln x over x cubed. And that would be your answer. All right, last two. These are fun. Now, they can get complicated because a lot of students will try to do this with like a U and a chain, and then they'll do 1 over this, and it gets complicated. But you need to remember what we did with logs in like a pre-calculus course. Always, always, always try to expand your logs. Expand your logs. What does that mean? So remember, we would rewrite this as ln of 2x plus 1 to the 1/2. And what are we allowed to do with that power? Well, we're allowed to bring it to the front, right? So this would just be 1/2 ln of 2x plus 1. So what we can do now is take the derivative of this. This is, again, this is a number. This is not like a 1/2 x. This is just a number 1/2. So we can just carry it along with our derivative. So let's take a derivative. So I would keep the 1/2. The derivative of ln of 2x plus 1. Well, what is that? That's the same rule we've been doing. You put 1 over that, and then times the chain of this. The chain of 2x plus 1 is 2. And so what can cancel? Well, this 2 and this 2 can cancel. Not that one. That's a quantity. Okay? But this 2 and this 2 can cancel, and your final answer would just be 1 over 2x plus 1. So it actually is so much more beneficial to expand your logs. do all those power rules we did before. So like number 6. Oh, this looks so messy. It looks like I'm going to have to do a product rule with a U. No. Expand your logs. If you were to expand the multiplication of logs, remember that? It's addition. This would be the same as rewriting it as this. ln of x plus ln of x squared plus 1 squared. But then what can I do with that 2? I can bring it to the front. So it's the ln of x plus 2 ln of x squared plus 1. And now I'm going to take the derivative of each one separately. So what's the derivative of ln of x? Well, it's just 1 over x. What's the derivative of 2 ln of x squared plus 1? Well, you got to attach that 2. The derivative of ln of x squared plus 1 is 1 over x squared plus 1, and then times that chain. So this would be 1 over x plus 2 times 2x. These are both in numerators. 4x over x squared plus 1. And I'm actually good with that. You might want to make it one fraction. We will eventually need to. If you remember your fraction rules, when they have 2 different denominators, you have a common denominator, and you just crisscross multiply. So x squared plus 1 plus 4x squared. So really, a better answer would be 5x squared plus 1 on top over x times x squared on the bottom. I hope that was helpful.